Hello. Uh, we are going to talk about incidence matrix. It's a completely new matrix, very different, not to be confused with adjacency matrix. It's also interesting. So this is a second part of algebraic graph theory. So let's make some definitions in the first part of today's class, and when we meet, we will explain some proofs of central theorem. So, incidence matrix. So this time, I think this is the only time that we are going to talk about multiple graphs. So there is a chance that we allow two vertices have multiple edges. Also, we talk about digraphs, directed graphs. It's possible to talk about undirected graph for this incidence matrix, but somehow it's more natural to talk about directed graphs, because you can imagine a sort of flow, either water flow or circulation flow or circuits to understand how what we want to do. Okay, so let's let G be a graph with directions, with orientation. So we probably put A and so arcs. Okay, so let me say V and vertices and arcs. So instead of E, we put arcs with directions. Okay, so we can list all the vertices. For example, we have V1, V2, Vn. You have n vertices, and the set of arcs will be, let's put A1, A2, but I think I like E1, E2, and EM. Okay, so I don't. So maybe I don't use A1, A2. So remember here, E1, E2, they are oriented vertices, edges, so they are arcs. So for example, we have V1, V2, we have this arc, which we say it starts from V1 and it ends at V2. Okay, so we are in the setting of a directed graph. So now we are ready to define this so-called incidence matrix. So it's in this setting. So let's put M. So is a n times M matrix. Okay. So we can use -1 or 1 or 0 to put into coefficients entries of this matrix. So more precisely, Mij in the position Ij, it will be 1, -1. Okay, if Ej starts at Vi, okay, it is 1 if Ej ends at Vi. Okay, so J, the column of the matrix will be related to edges. Okay, the row of the matrix will be related to vertices. So if they have no relation, we define this entry to be 0. All right. So what is going on? Let me see an example which is makes things clearer. So let me draw this graph. You have this edge arc E1 and have another arc E2. So we allow the two arcs to join the same starting vertices and ending vertices. And here you have E3 from V1 to V3, and you have E4 from V3 to V2. You have E4 here. Okay, so V in this example will be V1, V2, V3 have 3 vertices, and the set of arcs will be E1, E2, E3, and E4. Okay, so we have 4 arcs and 3 vertices. The matrix D will be a 3 by 4 matrix. So 3 here by 4 matrix. So it will be like this. The first row represents what happens to V1. And you observe all these 4 arcs. E4 has no relation with V1. So E1 arrives at V1, you put 1. E2 arrives at V1. E3 goes out V1, so put -1. And for V2, we have something similar. So it goes out, E1 goes out of V2, so we have -1. And E2 also. E3 has no relation. E4 get into V2, so we get this. So V3 for V3, both V1 and V2 has no relation. Both E1 and E2 has no relation with V3. And E3 goes into V3. E4 get out of it. Okay? Something like this. So this is M of D, the matrix M. Sorry. Okay. The D. Sometimes we use D to denote the directed graph. Okay. So this is the incidence matrix. Right? So next, we are going to look at this incidence matrix. We will study the space of all real functions over all the edges of the graph. Let me explain. For example, we have a graph with 2 edges. I want to assign some numbers here. So probably this is edge, arc E, arc F, maybe E1, E2. I want to define a function such that Fe1 equals something and Fe2 equals something. Okay? So the space of all the functions, because we have, if I put M to be the number of arcs of the graph D, so this space of all real functions is actually, so this space of interest is actually, so this, the above space is indeed a vector space. And the dimension is exactly M. Okay? So here is the thing. We have to relearn what is a vector space. A vector space, I will write a little more details in the notes. So here I just repeat with words. A vector space is just a bunch of vectors, what we call vectors, such that there are 2 operations. So we have a vector space V. Then if you take V, WV, two vectors here, you can make sums. So this is well defined. You take the sum, it does not come out of the space. So we say that the space is closed by summation, by making sums. And if you take any vector here and any number in R, in general some field F, but let's only talk about R. So this is something we call scalar. It's just a constant. Alpha W also belongs to V. So vector space allows you to make multiplications by some number and also make sums. Okay. So when we start to learn linear algebra, the major task is trying to solve certain linear equations. So we call this a system of linear equations. And the first equation we want to understand is this. Okay, this is something we call homogeneous equation. Okay, so to solve this equation is just ask what kind of x will give you a solution. So for example, we have something like 1, 2, 3, 4, 5, 6, whatever, and you get x1, x2, x3 equals 0. We trying to solve this means exactly to find x1, x2, x3 such that this is 0. So for this system, in order to solve that, we are interested in this so-called null space, which we define n of a to be all the solutions x, for example, equals x1, x2, xn, okay, such that a of x equals 0. So it's a solution space. It's just the solution space, and sometimes we call it null space. Because if you think of x as a vector and a as a kind of a linear operation, it will annihilate x. It acts on x, and the result gives you a 0. So we call this a kernel of an operator, and also we call this null space. There are many names. Okay, so we are interested in this. So if eventually we will find what is the null space of our incidence matrix M. Okay. So it's a little review of linear algebra. It's you have to learn, you have to know linear algebra to do this. Okay, if you don't know linear algebra, it's gonna be tough. So I cannot repeat all one semester theory, but this is really very starting point of linear algebra. If you ever learn linear algebra, you have to know this. So we here it comes some more definitions. Let's come back to graphs. So if remember we have a directed graph. Then we want to define something called a circulation. So it's like a circuit. You can imagine a circuit or a flow or water flow. Okay, so let's actually, this is the actual graph theory notion. So a circulation is a function, is some function f from all the arcs to R. Remember, I said I'm interested in all these kind of functions on the defined on the arcs. But the circulation is special, so it has to satisfy that for every vertex V in V, every vertex V in V, the sum, I write a very long sum, okay, of all edges such that E starts at V for every V. Okay, V is fixed. So for example, V is here, and I saw some arcs starts at V, and I also see. Let me put another color. See some arcs which ends at V. Okay, so we have a group of edges that starts at V, and I put f of V. Okay, this is definition. I need to find the function here f such that this is on the left hand side. It equals the sum of all the edges such that E ends at V and f of E. Okay. So what happens? For example, I have 1, 1, 1 here and 1, 1, 1 here. Okay. For this V, this equation is satisfied. But for f to be a circulation, it has to satisfy this for all V. So why we define such a thing? It seems complicated, but it's natural. So what happens is that you imagine there is in our directed graph, every edge, you imagine there is a number there. Okay, so when this number 1 is assigned here, it means that some flow with this speed is going out of this vertex B. And this red arc, you put 1 here, it means that something, water or circulation or circuits or electricity or something is flowing into this vertex B. And we want a sort of a balance. The total amount of water get into it equals total amount of water getting out of it. Okay, so there is a kind of a real life way to imagine these notions. So okay, right. This is the basic notion, and okay. So we are going to show that the kind of circulations are very special functions among this inside this space of all functions. Okay, so here is all the. I think here is enough. We can try to prove something during the class. So so this ends my preparation recording for today.
So um, it's a little non-trivial. Today we are going to talk about something not very trivial. So let's recall the definition of actually it's here, a circulation. So circulation, let me give an example by complete this definition. It's something like this. So for example, we have a graph like this, something like this, and you have a arc, and here is 5. You put 5 on this arc, and maybe 2 here, and maybe this is this direction, this orientation. So you have this 3 here. So in particular, if you look at V, so there is 5 going out, and 2 going in, and 3 going in. So you see, so the sum of out degree weighted, some sort of weighted out degree equals the sum of the weighted in degree. So you can imagine this F to give weight on each edge. But I want to remind that you can also put a negative value. So for example, this one, and then you have this one fall here. So okay, so you have to consider this out value, which is 4, and this out value, which is -1, and together it has to equal this in value 3. Okay, something like this, and something like this, and something like this. You have 7 here, and what is here is a -6. So this is just an example. Okay, so I want to remind that you can take a negative value also. This is a circulation. I mean this function defined on all the arcs. So this function is a circulation. So you can imagine that there is a sort of a circuit. Electricity goes around this graph. So so we have weight 3 going in here and going out 5 here. So you also can think of these kind of pipes with waters. Doesn't it's they're all the same. So we use mathematics to make all these kind of abstraction. Okay. It's not very difficult. So all these to prove that this exercise. So all these functions they form, indeed, all these functions. All these circulation functions is a subspace. So it's a subspace of all functions. So I mean, what is subspace? So if you have a big space V, which is just R to the power of M, M is the arc number. This is the whole space. Okay, for each arc, you can put a value. So all the functions, you can identify them with this vector space. And the circulation functions, they form a subspace of all the functions. So they are kind of so to check some spaces subspace this space itself. First of all, this set as a subset, it is a subspace itself. It's a vector space itself, and then we check so all the operations. For example, V1 plus V2. If you take V1, V2 inside this subspace, the sum also belongs to the subspace. We say that this addition and scalar multiplication, they are closed inside this space. That's the subspace. Okay, so let's see another example. Suppose we have a cycle. So by a cycle is a directed cycle. By a cycle, I mean a cycle as a graph with an orientation. For example, I draw a cycle here. Okay, so we have V1, V2, V3, V4, V5, and so on. So this is a cycle. Maybe we write denoted by C. Maybe we use C to denote this cycle. And so what I want to say is that this cycle it defines a function, what we call FC on A. So okay. So I actually it's on A. And I want to prove that it is circulation. Okay, so note that this cycle has an orientation. So this cycle is an orientation. Okay, so I draw it like this. So this is a cycle, my cycle C, and with an orientation. Okay, so look, so for example, if I have a complicated graph, and this graph may be something like this, okay, and I draw this cycle, this graph has an orientation. So maybe something like this, and this, but this direction is not exactly compatible with my cycle. My cycle, if I put an edge set, for example, a copy of C4 here, there is a possibility that the orientation of the graph and the orientation of the cycle are not the same. So they could be the same, and they also could be not the same, right? So what, by definition, my function FC is like this. So for any edge, for any edge E, my FC of E, I want to determine its value if E belongs to my cycle. And the orientation of E in my cycle and in the graph, what I call D, are the same. If they are the same, then I define FC of E equals 1. Is it definition clear to you guys?
Yeah.
Right, great. So I have imagine I have a cycle, and there is kind of, or maybe I should put names. Maybe this orientation of the cycle is called O. Put O, big O, orientation. And I'm saying that if the same edge in O and in the orientation they have the same direction, and I put this function as 1, and otherwise, if E belong to C, and the orientation of E in C and in the cycle, so and in the graph D are opposite, exactly different. So this goes this way and the other goes the other way. So in this case, I put FC of E equals -1. So it's kind of you go in the opposite directions. And finally, if E is not one of the edges of C, I just put FC of E equals 0. So I have this kind of definition of F of C. So you can track that this FC is an orientation. It's not so hard. Okay.
If E is not in C, or if E is in C.
Can you repeat the question?
If E is not in C, or if E is in C, because
okay, it's not. Sorry, it's not. Thank you. If E is not in C, I put it equals 0. So maybe I have some graph like this. Let's see. Okay. Something like this. This is my graph, and this is my cycle C. My cycle is, I cannot draw this. My cycle is just this guy. This copy of C4, right? This is my oriented cycle. So then I see that my FC, this is my FC value. This is 0 because this does not belong to my cycle, and this is 1, 1, 1, and this is -1. Okay. Right. So you see, I think it's not difficult to track. So this in degree is 1, out degree is 1. So this in degree is 1 also. So this they have a problem. They don't have out degree, right? So out degree is 0, but in degree is also 0 because you have to put a 1 plus -1 at this point. So it's a circulation. So basically the idea is this, and you can track, you can discuss and prove this. It's an exercise that FC is always defined this way, is always a circulation. So why it seems a little complicated here, right? But what's going on here is that it gives you a way to understand cycles. So in a directed graph, you take any cycles like this, and somehow you get a function. And this cycle, if you try to use this function to represent this cycle, you get a space which we call cycle space. Actually, this space is a subspace seen as this subspace of R to the power of M. This subspace is generated by all the FC. And next we are going to prove something. Okay. So before that, let's see a further definition. Okay, so we see we have seen a definition about function on edges. Now we take a function. We take a function. Sometimes we take a function on the vertices. For example, phi from V to R. So this is a function on the vertices. So there are finitely many vertices, and they assign a number to each vertex. And every such a function is called a potential. So imagine you have some potential energy on all these points if you have this circuit. But anyway, here we get away from physics. We just define all these definitions in mathematics. So here is a function f, so phi. So it's called a potential function. Potential function. Okay, so phi is a potential function. Okay, any function is called a potential. But I'm interested in the following thing. So I'll define something called a co-boundary operator. So it's to be honest, this kind of thing could be very deep. But here it's not difficult to understand. Believe me, it's not very difficult to understand. Actually, it's one of the best ways to define such a deep thing at the early age in the whole mathematics. So co-boundary and the boundary operators, these are essential in algebraic topology. Okay, but here it's really simple. So what is an operator? Operator is that you give me a function and I produce another function. So this co-boundary function exactly does that. So input start with a potential function. Which is defined this way. So phi is from V to R. So it's a function on these vertices. Then we obtain delta. So usually co-boundary or boundary use delta or delta. This kind of notation. Delta of phi. So this phi is given, and delta of phi is a function on the arcs. On all the arcs. Okay, by definition, for any arc W1, W2, you see if you have an arc here, W1, W2, delta of phi, the value on this arc is equals phi of W2 minus phi of W1. Okay, so it's a difference of the potentials. So in other way, delta of phi is exactly potential difference. So imagine if you have the potential energy here is higher and here is lower, the difference is the potential difference in the language of physics. So for example, if you put a 1 here and 3 here, then this edge, I say it has a potential difference 2. Okay. So I don't think it's a really difficult definition, is it? Let me put an example. Let's put example this guy. So this is the example I just used earlier. So let's say this is so for example, I put some potential function. So here I put a value 2. So I forget about names of these vertices. It's not very complicated. So here is a -1, say, and 3, and 0, and 5. Okay, so I have those things. Okay, so but I want to put because I have a graph with direction, so I define all these orientations. So I have this direction, and maybe okay. So what is the number here? I should assign. So this is I already give you the function of the potential on all the vertices. So what is the number on this edge? This will be the value of this guy minus value of this guy. So this is 4 here. Okay. So this is 0 minus 1, which is 1. So this is 5 minus 0, which is 5. So I didn't give a direction here. So for example, here, then this gives me a minus 3, and this gives me a 3, and this gives me a minus 3, something like this. Okay. Right. Okay. Let me check here something. Let us please check. Is it a circulation? I put it too difficult. Let me forget about this. So maybe this one is easier. So check this vertex. It's just I think this is a coincidence, but anyway, this is easier. So let's check W. The in degree is 5, out degree is minus 3. So it's not okay. So they are not equal. So this is not a circulation. So this space is kind of a complementary space. It's orthogonal to the circulation space. Is exactly all the rest of the circulation. So unless you put all potential 0, 0, 0, everything is 0, right? So let me try. Let me try to do this. So okay. So let me define now. Define B to be the space of all potential differences. So imagine you define all the potentials in arbitrary way you like, and then you obtain a potential difference, and you put together all the potential differences, and they generate a subspace, and this space is B, and we call it the bound space. So why I use a strange word bound is actually it comes back a familiar topic. Is in the world of directed graphs, bound are kind of a minimal cut edges, minimal edge cut size. It's so let me introduce a definition. So it's something we already discussed. So given let me definition. Given a graph G, we have, for example, V, and arc set A. A bound, so it's a directed graph. A bound is a minimal edge cut space. Minimal edge cut subset. Cut set, let's say cut set. So by minimal, I mean there is no proper subset which is also a cut set. I think this kind of thing are easier to put in examples. Let me write some. You see some. Okay, something like this. So note that this definition can also okay. So okay, usually it's for directed graph. Okay, so let's draw a directed graph. So this E1, E2 are two edges here. These edges have no names. Maybe you have E3 here and E4 here. Okay, something like this. And maybe you have something other things. I don't care. And I try to understand this. Maybe okay, maybe not. Maybe like this. So let me see. So this is my graph. Is it the graph clear? So something like this. Maybe I don't know. So, but E1 have a set of edges. E1, E2, E3, E4 is a set of edges here, right? So this guy is an edge cut. Okay, if you delete them, the graph becomes several disconnected parts. So if you delete all of them, the graph is disconnected. So in this case, we call this an edge cut. But it is not minimal because what? If you consider E1, E2 is also an edge cut. It's okay. So imagine if I only cut E1, E2 here, the graph is disconnected already. So here is an exercise. Exercise. Actually, this is exercise in the book. So exercise. So a set X of vertices, subset of vertices, and then look at X and V minus X. So in this case, you have this and the remaining vertices. So whenever you look at some subset X and the remaining vertices, you can look at all the edges between these two subsets. Then B is defined as the edges, all the edges between X and V minus X. This is fine. So the exercise says that B is a bound if and only if and only if both G induced subset on X and the induced subset on V minus X are connected. So I think this is a very, very interesting exercise. I encourage you. I'm not sure. It's a possibility I will put it in the list. But I will think about it. Maybe it's a little too difficult. I will think about if this is appropriate. But if you have extra time, I encourage you to think about this exercise. In this example, this very special example, this E1, E2, E3, E4 is not a bound, because if you cut it like this, the graph becomes 3 connected components. In particular, this part is not connected. So it's a matter of tracking definition and some extra effort to prove that this set exactly is separate. The set B of edges, which goes from X to V minus X, it is a bound if and only if both parts are connected. So if you delete this bound, the graph becomes exactly contains 2 connected components. Okay. So this is a good exercise to understand all these extras, all these properties, all these definitions. Then given a bound, let's say between, I think it's enough to say a bound is between X and V minus X. Okay, so I have a new definition here. So suppose we have a bound, then it induces a function GB. So this is very much similar to how a cycle induces a function. So here bound also induces a function on the arc side to numbers. So we have a function GB from the arc side to the outer numbers. The definition is as follows. So GB of some arc E, it will equal to 1. So it's very similar to cycles. Look, if it equals 1, if E belong to the bond, okay? It's a part of the bond. And also E is from X to, for example, V minus X. So imagine you have X here, and this is V minus X. And for some edges, it's this direction, and some edges is this direction. So this direction you assign 1, this direction you assign -1. And other edges 0, okay? So -1, if E is a part of B, and E is from V minus X to X, so the other direction. And it's 0 if E is not part of B. Okay, for example, this E. So this is the definition of function given by a bond. So here, recall, we have a lot of definitions, but the principal one, sort of, cycles and bonds. So give you a cycle, you can start to build a function. Give you a bond, you can build a function. So these two functions are kind of orthogonal. So if you think of them as in the vector space. So this is exactly what we are trying to prove. So we are going to prove two theorems. Okay, so one remark. I think it's interesting to make one remark. A bound function is actually a potential function. So GB is actually a potential difference. Actually, a potential difference. It's not very difficult to show because I want to put my phi, all vertices here with value 0, all vertices here with value 1. Okay, so in this way, by definition, any edge here has to be signed 1 minus 1. So any edge here is 0 minus 0. So all edges here are 0. But this edge is assigned number 1 minus 0, which is 1. And this edge is assigned with 0 minus 1, which is -1. Okay, so GB is actually a potential difference. Okay, so now we are ready. We have all the players now. So we are ready to prove this theorem. Let D be the graph. We have V and arc set. And it has the incidence matrix M. So we write M as it's an incidence matrix, which is N times M. The row number is the number of vertices. Column number is the number of edges. Then the row space. What is the row space? So the space, the vector space generated by all the rows of M. So if you write this as some rows, so this is a vector, this is a vector, this is a vector, this is a vector. You use all these vectors to generate a space. We call it a row space. Okay, I don't want to write down this. So the row space of this matrix is exactly the bound space of B of the graph. Okay, so the incidence matrix, take any row here, for example, the first row, and you look at it. So it's a subspace. It's a vector in R to the M. R to the M actually is the space of all the functions on edges. So here is a one vector inside this vector space. And this vector, not only this vector, actually the space generated by all rows are exactly the bound space. Okay, so let's prove this theorem. So the proof is it's not very long, but it requires you to reflect correctly to all these definitions I gave. The definitions are complicated, I understand. So I hope you can take a read of this later. So, but now let me explain. So let's look at one vertex V, and you can imagine it has some edges going out of it, and maybe some edges going out of it, and some edges going into it, and maybe some more. So let's call this E and call this F, say. So for any, this is for any choice of V in the vertex set. Okay. So we get a very simple bound. We get a bound which, okay, so it's not necessarily a bound, but suppose it's a bound. This is a poor idea. Okay, it's not. You have to make sure of a few things, but the main idea is this. So we get a bound which separates V, which separates the set V and V minus V. So V with all other things. So we just, so this is at least is edge cut, but it's not necessarily a bound. Okay, maybe you have some component here, some component here, but it's fine. So let's suppose V is a bound or not, and call we will define. So in many cases, we can define a bound. So there are several cases we cannot define a bound, but but in that case, you can see it's a linear combination of several bonds. Okay, so suppose a bound. Then we look at this vector mv. Okay, so this mv could be the corresponding bound. Okay, for this separation, to separate v and v minus v. So for example, E mv of E is 1. Remember the definition of bound here, right? It takes value 1 minus 1 or 0. Okay. So mv, so this has a relation with v of f is minus 1. If imagine you have an edge here, which you call other things. So for example, f prime. So mv of f prime clearly is 0. It has no relation with the vertex v. Okay, so this is the definition of m of v. Okay, so let me prove one direction. So I want to show that I'm saying this is a bound. The row space is exactly the bound space, right? Bound space, by definition, is generated by all the potential difference. Remember, I defined this before the definition of a bound. B, this is the space all the potential differences. So I take potential difference. I want to prove that it belongs to the row space. So take a potential difference, which I write G. Okay, so a potential difference is a boundary, co-boundary of some phi. So phi is a potential, and I make this operator, and I get this potential difference. So suppose G is a potential difference. So this is my potential difference, and I want to prove that this G belongs to my row space. So why is that? For any arc, for example, E equals W1, W2. So let me draw this. We have this E. We have a direction. This is W1, W2. G of E is phi of W2 minus phi of W1 by definition of a co-boundary. Okay, G is a co-boundary, it's a potential difference. Phi is a potential. We have this. So there is a very interesting way to write this. So this is a sum of all the vertices x such that phi of x times m of v of m of x of e. Okay, can you track this? So this is a little strange because here it's just phi W2 minus phi W1. Okay? But in this sum, it seems to have many terms, but eventually you only have two terms. Because this m of x only takes value non-zero when W1 or W2 is related to this edge E. You see, for example, when we are looking at x equals W2, okay, it's one of the sum, right? So I want to first see this term is phi of W2. And this guy, what is that? M W2 of E. By definition of M of W2, because E is arriving at W2, so this is 1. Another term, if I look at x equals W1, and this phi, we get phi of W1, and times multiplied by this M W1 of E. What is M of W1 of E? It is minus 1 by definition, because how we defined M W1. Because E is an edge which going away from W1. Then this takes value minus 1. So this sum, although I write a sum like this, it's a little strange, but actually only two terms here are not 0. So for other vertices, here, for example, I have edge E is here, but I have some other vertex x star. So when x equals x star, this guy is 0. So it doesn't appear in the sum. But why I write this like this? Because if I write it like this, I see that G actually equals this sum. You see? Oh, because if you see, equals this sum. So G of E equals, this is like coefficient, and you have M of X of E. G of E equals this sum. This is the coefficient of multiplied by M of X of E. Okay, so here is a little involved, but it's just definition. Okay. So what's going on here? So G is so how to understand this? So G is a linear combination of each mx. So you have mx for all vertices. You have mv1, mv2, for example, and the phi of x is like the coefficients. So what is mx? Why we conclude? Why we already finished the proof? Each mv for v in V represents a row. Exactly a row in M. So what is the, let's come back to the definition of incident matrix. What is this? M. So look at this row. This row represents a vertex. So if this edge going out of V, you got 1. If this edge going, you see, if this edge E2 arrives at V, you got minus 1. So this vector is exactly how we define this vector here. So I should maybe I should remind you earlier. So this MV exactly is the row in the incidence matrix which represent your vertex V. So this row here, so this is my M. Okay, so now given any potential difference G, I have been able to write it as a linear combination of all these rows. So it concludes that G belong to the row space. Okay. As for the other direction, it's easier. It's not more difficult. So for this direction, so if G is really some x in V of mx, and you have, for example, cx, some cx like coefficients, because I mean, if G belongs to the row space, it has to be able to, you have to be able to express it using some coefficients with these row vectors, right? And then actually by all these arguments, we see that G is actually a potential difference for the potential function what is the potential function? Exactly Cx, okay? From x to Cx. This is the function on vertices. So they are related like this. It's not a long argument, but I think it's pretty nice and it's pretty advanced. Okay. So now we find this potential function. All these things are standing very closely together. So you try to know these objects and understand it in different ways. Okay. This is the first theorem I want to prove. The second theorem, which is shorter, but the first theorem is more difficult. So the cycle space, which we introduced firstly today, actually is the null space of M. What is the null space? All the solution space. What is the null space? All the solution space of mx equals 0. So it's so take f, which is a function. Remember that f is a circulation if and only if what? For any vertex. So we have stated this exercise. So the in degree short of equals the out degree, but I want to write it in another way. So for any vertex, remember MV is what? Is this row, right? So you have E1, E2, and the 1, maybe minus 1. 1 means that the edge is arriving at V. Minus 1 means that the edge is going out of V. Right? So what is the equivalent statement for circulation? So the sum of all these values of f on these edges arriving at V equals the sum, right? The sum of f values on all the edges, arcs that are going away of V. Right? Remember, this is really early, way early. We first thing we talked about today, this thing. I need to use this thing. So remember, this is a definition of circulation. So if we move the right-hand side to the left-hand side, we get minus this equals 0. So all I put plus minus 1 times this guy, right? So this big sum plus this big sum times -1 equals 0. So this is exactly this thing. So you have several -1 and several 1. 1 counts all the situations that you are arriving at V. And the -1 counts all the situations that you are leaving the vertex V. So if I got M, this is my M, and this is one of the row in my M, and times x1 until xn equals 0. In particular, this row I got, for example, this row at least, this row is L1, L2, Ln. Okay, so I need to solve this x1, xn. So right, so I think it's better to write it here. So I pick one row here, the same row. I write it as L1, L2 until Ln. And this product gives you, so x1, L1 plus x2, L2 plus until xn, Ln equals 0. So it means what? It means that your x1, xn solve, because this is true for all rows, solves is a solution. And at the same time, if this equation is satisfied, it is by definition is equivalent to F is a circulation. So it's equivalent with our equation here. All edges such that E starts at V of F of E equals all edges such that E arrives at V F of E. So this equation, like I said, I'm doing it again. So is equivalent with plus -1 times this equals 1. And all this -1, it represents this -1 here. All this here, maybe there is a 1, 1 represents 1 here. So it translates. So the same formula, we gave it multiple meanings. Okay, this is the definition. This is the proof. Okay, so this concludes today's class. Okay, so I try to in your list, I try to think about it, how to make the task simpler for you to do. But I take the chance to explain something really really difficult, really deep for you. So this kind of relation, using algebra, linear algebra, and assign meanings to the different vector spaces is far-reaching. It's very difficult. It's very nice stuff. I'm not an expert here. I'm not an expert here. It goes far beyond this course, and there are a lot of active research going on here. So, okay, I hope you enjoyed. Okay, so let me. This is all I want to talk about in today. So let me finish the recording.